Next, we're going to look at orbital energy level diagrams. So what an orbital energy level diagram is it's really just electron configurations, but represented in a picture. So in this picture here, you can see the nucleus at the bottom here. From there, we label the electron configuration orbital energy levels. So notice the energy is increasing as we go up. So we're going to start at the lowest energy level, which is 1s. We next then go up to 2s, because if you look at the periodic table, after the 1s, we hit the 2s next. From there, we follow along in period 2, and we hit the p block next. So 2p. Once we're done in the p block, you'll notice we then get to period 3. We always hit the s block first because s is lower in energy than p. We then hit the p block. Next, we go and hit period 4, hit the s block first. Notice then we're going to hit the d's for the first time. And the d's are always one less than the period they're in. So you'll notice this says 3d instead of 4d. The reason for that is because the d block is one less than the period it's in. So we're in period 4, so that means it's going to be 1 less 3. After the 3Ds, we hit the 4Ps and then continue on our way. So when we're filling in one of these maps, you're going to start at the lowest energy level and work your way up. There are some rules on the following slide that are going to help us fill these in. Now, you won't need to fill in one of these particularly, but you will need to know the rules and be able to recognize one that is filled in. So let's look at the rules to fill in an orbital energy diagram based off of its electron configuration. Now remember, the number of electrons in a neutral atom is equal to the number of protons. We're going to be using the next following 3 rules to fill in an electron configuration, and I'll show one of these in class and how we fill it in. So the first principle, the Aufbau principle. This principle tells us that electrons fill the lowest energy orbital first. So that means we're always going to start with the 1s and work our way up. The Pauli exclusion principle says that no more than 2 electrons in each orbital. And we already said that there's a max of 2 electrons in each orbital. So what that means is when we put electrons in an orbital is usually represented just by an empty space on those orbital maps. That means we only want 2 electrons in each space, no more than 2. Hund's rule tells us that when we are filling these in, that each subshell should become half filled before any become completely filled. And this only applies to p and d orbitals, because p and d orbitals, or p and d subshells, have more than one orbital. So looking at this p orbital here, notice p, we said, has 3 orbitals. There's a max of 2 electrons that can fit in each. But if we don't have 6 electrons to put in the p orbitals, say we have 3 instead, what that means is we want to put just 1 electron, represented by these arrows, in each orbital before we start pairing them up. Because electrons are negatively charged, they want to be as far apart as possible. So we want to make sure to give them the space needed. So we're going to take these rules and these definitions, which you should know for the exam, and apply them in class when we're filling out an electron orbital map. So watch that video for further explanation of these rules. Here's an example of a filled orbital energy diagram. So we can actually figure out, if this is a neutral atom, what element this orbital energy diagram is representing. So looking at the electrons, so starting in the 1s, notice there are 2 electrons in the 1s, a max of 2 electrons. Notice also the electrons, we have one pointed up and one pointed down because they must have opposite spins when they are paired. And that was part of the Pauli exclusion principle. Moving up, the 2s orbital, once again, we have a max of 2 electrons. Next, we get to the 2p orbital. And notice it's completely filled with 2 electrons in each orbital, a max of 6. The 3s, once again, s orbitals with a max of 2. And then when we get to the 3p, notice it's not completely filled. It doesn't have the max of 6. Instead, we have 1, 2, 3, 4. So what this means is it can be represented by an electron configuration of 3p4. So if this is a neutral atom, looking down here, we would look in period 3 in the p block, and it would be the 4th element in. So looking at my periodic table, the 4th element in the p block in period 3 is sulfur. So if this were a neutral atom, it would be representing sulfur. What we have in the diagram over here are just the electrons and how they would be filling an atom. So we have the nucleus in the center. Each ring represents the principal energy level. So we have 1, 2, 3 principal energy levels representing this 1, 2, and 3 here. And the x's are the electrons on each of those levels. So in the first level, we have 2 electrons represented in the 1s. On the second ring, the second level, we have 8 electrons representing the 2s and the 2p. You can count them for yourself to prove it. In the very outer shell, n equals 3, the outer ring, notice we have 6 electrons or 6 x's represented. Now let's talk about valence electrons. So when we talk about valence electrons, we're only talking about the main group element, or the representative elements that we looked at on the periodic table when we were looking at groups. The valence electrons are the outermost shell electrons. They have the highest energy level. They have the highest energy level because they are furthest from the nucleus. So the reason that electrons orbit the nucleus is because the nucleus is a positively charged center and the electrons are negatively charged. So that attraction between the positive and negative charges holds those electrons close to the center, attracts them to the center nucleus, and allows them to orbit it. So the further those electrons are from the center, the higher energy they have because they're not held as tightly as the electrons that are closer. The number of valence electrons in each element is going to correspond to the number of the group that they are in. So we can figure out how many valence electrons an element has just based off of where it is located on the periodic table. So looking at valence versus core electrons in an orbital energy diagram. So the valence electrons we said were the outermost shell, the highest energy level. So that is going to be these electrons here in level 3, the principal energy level 3. So in this particular atom, there are going to be 6 valence electrons. We can also see that when we look at this outer ring in the representation of the atom. So those electrons in that outer ring, those electrons that are furthest away from the nucleus, are going to be the electrons represented in the yellow box over there. So they are the valence electrons. Notice there's also 6 of those. The core electrons then are going to be all the other levels. So the rest of the electrons left over. The ones that are closer to the nucleus, held more tightly, and have less energy. So valence electrons and the octet rule are very closely tied together. So what the octet rule is, it says that elements want to be a noble gas. That's the basic gist of it. So it's called the octet rule because elements want to have 8 valence electrons. Once they have 8 valence electrons, they are happy, they are stable. Now, there's always exceptions to every rule, and you'll see that throughout this semester in chemistry. So hydrogen and helium will have less. So helium wants 2 valence electrons because that's all it can hold, because helium is in the 2s subshell, and we said S has a maximum of 2 electrons. However, the rest of the elements want 8, hence the term octet rule. Because if they have 8 electrons, they are in a noble gas state. And when we talked about noble gases, we said that they were stable, they were inert, they were unreactive. This is because they have a full outer shell, a full valence shell, 8 electrons in their shell. They don't want any more, and they don't want to give any up. They're happy. So all the other elements on the periodic table, their goal is to be happy just like the noble gases. In order for atoms to gain a full octet, in order for them to be a noble gas state, they're going to have to gain or lose electrons to get there. Now, when an atom gains or loses electrons, it becomes an ion. So what an ion is it's basically an atom with a charge. If an atom has a charge, that means that its protons no longer equal its electrons. We're not neutral anymore. Atoms that form ions have 2 different names. One is an anion, the other is a cation. So an anion is when an atom forms a negative charge. So it's called an anion because it has a negative ion. The cation then will be when an atom gains a positive charge. So a way to remember that cation represents the positive ion is this little mnemonic device here, where you see a positive ion, spelling out cation. So we can actually use the periodic table to predict the charges of ions. Remember, the reason that the elements on the periodic table form ions is because they're trying to get a full octet. They're trying to be a noble gas. Now you're going to notice trends with this. You'll notice that metals tend to lose electrons and become positive. So this is a little counterintuitive because usually when you lose something, that's not a positive. But remember that what they're losing is electrons. And since electrons are negatively charged, if you lose a negative, you will become positive. So let's remember where the metals are in the periodic table. So here's the zigzag line separating the metals from the nonmetals. Remember, the metals are off to the left-hand side, the nonmetals to the right. Everything touching is going to be a semimetal or metalloid, with the exception of aluminum. So, looking at the metals off to the left, notice all the charges that you are seeing here are positive because they all form positive ions or cations. The nonmetals then, off to the right, my directions mixed up. The nonmetals tend to gain electrons. So if they're gaining electrons, they're gaining negative charges. So they themselves will then become negative. So notice all the nonmetals to the right have negative charges. Also notice the nonmetals in group 18 here are the noble gases. This is the goal that all the other elements are trying to achieve. The reason those elements have no charges is because they already have a full octet and they don't need to gain or lose anything to be happy. They already are. So let's look a little closer at these trends. So if you were noticing in the previous slide, group 1, the alkali metals, which include all of those elements except for hydrogen, because hydrogen is a nonmetal, they always form +1 cations. So they like to lose 1 electron to gain their octet. Group 2, the alkaline earth metals, always form +2 cations. This is because They like to lose 2 electrons to get their full octet. Then moving all the way over to group 17, which is right next to the noble gases, those nonmetals like to gain electrons. So since they like to gain electrons, they're going to form a negative charge. In this case, they all form a -1 anion. That is because they gain 1 electron to become noble gas state to get their full octet. The transition metals can form multiple charges. So they don't have one in common. It just depends upon what they're combining with. This is going to bring now a new term, the term isoelectronic. And what isoelectronic means is the same number of electrons. So core and valence electrons together. Atoms that form ions want to become isoelectronic with the nearest noble gas. So that's how we're going to figure out what charges the main group elements, at least, will form. So predicting charge. So here's a table showing the fixed charges of the main group elements. Notice variable charges in blue here. We're looking at the transition metals and some of the semi-metals. So the reason that those are variable charges is because they can form multiple different charges. We can't predict what those charges are based off of where those blue elements are on the periodic table. However, the elements in white, the fixed charged elements, those elements will have that charge to fill their octet. They will have that charge in combination with other elements all the time. So we can predict those charges based off of what those elements are on the periodic table. For instance, in group 1 here, the alkali metals, they always form a +1. So the reason these elements form a +1 is because they're metals, so they like to lose electrons. And in this case, what they have is just 1 electron to give away. So when they give away that 1 electron, they then become the noble gas in the row above them. So they have the noble gas state as the noble gas in the row above. Looking in group 2 here, the alkaline earth metals, notice they are always a +2. Why? Because they have 2 electrons in their s orbital. So when they give away those 2 electrons, they become a +2 charge, a +2 anion, and have a noble gas state at that point. Looking over at boron and aluminum. So aluminum is a metal even though it's touching that zigzag line. Aluminum is going to form a +3 charge because it's a metal, it's going to lose electrons, and it actually has 3 electrons in its outer shell. So if it loses all 3 of those electrons, it becomes a +3. Now group 4, we're going to ignore for the most part because they're special cases. But know that group 4 has 4 total valence electrons. Okay, now let's look at group 5. And I'm counting these just the representative elements. Notice I skipped the transition elements. Valence electrons are only applying to the main group elements. So group 5 here is going to have 5 valence electrons. So why do they form a -3 charge? Well, we said all the elements in the periodic table want a full octet, which means they want 8 electrons. So, since group 5 has 5 valence electrons, and it wants to get to 8, how many more does it need to get to 8? 5 plus what equals 8? 5 plus 3 equals 8. So that's the reason why this group forms a -3 charge, because they're going to gain 3 electrons to their already 5 electrons to have a total of 8. And when they gain 3 electrons, those electrons are negatively charged, so they're going to form a -3 charge. Next, group 16 has 6 valence electrons. The reason they form a -2 charge is because they need 2 more electrons to have 8 to be happy. Next, group 7, the halogens, always have a -1 charge. That's because all they need is one measly little electron to have 8 and have a noble gas state to be happy. So notice the nonmetals are gaining electrons to become negatively charged because they only need to gain 1, 2, and 3 electrons to get there. The metals, the reason the metals don't gain is because the metals only have 1 and 2 electrons. So they would have to gain 6 and 8 electrons respectively to get a noble gas state. And that's a lot of electrons to gain. So instead of gaining them, it's easier for them to lose the electrons they have to get a full outer shell. Then the noble gases have 8 electrons, except for helium, which just has 2. So we'll work on these problems in class. We're going to predict the ion that will form, and we're going to also use the definition of isoelectronic to figure out what noble gas they're isoelectronic with. Answers are coming up, so pause if you wanted to do those on your own. The last topic we are going to talk about are periodic trends. Atomic size is the periodic trend we're going to focus on most in this chapter. And what atomic size is the size of the atom itself, hence the name, but the reason that atomic size changes is because the distance between valence electrons and the nucleus change. In this trend, what we're going to see is it increases as we go down a group. And the reason for this is because the n values are going up. And those n values, remember, are rings around the atom. So the more rings we have around the atom, the larger the atom's going to get. We'll also see that atomic size tends to decrease from left to right across a period. The reason for this is that electronegativity actually goes up. So what that means is the electrons are actually held more tightly as you go across a period. So if the electrons are held more tightly, it's going to condense that atom down, making it smaller as we're going from left to right. So with this trend, we'll see that fluorine is the smallest of the atoms, and cesium is the largest. So the reason francium isn't is because francium is radioactive, unstable, so we're not including him in our trends. There are 3 other trends that we're going to discuss briefly, but it's important to remember atomic size, most important for this chapter. So ionization energy is the energy required to remove an electron from an atom. So the more energy it takes, the higher the ionization energy. We're going to see this decrease as we go down a group. So the atoms are getting bigger, we said, as we go down a group. So since the atoms are getting bigger, the valence electrons, those outer shell electrons, are further away from the nucleus. Since they're further away from the nucleus, they are held less tightly, and it's easier to pluck them off. So it's not going to take a lot of energy to take a valence electron from an atom, a large atom. We're also going to see it increase as we go across a period. So notice it has the opposite trends as atomic size does, due to how tightly those electrons are held. The more tightly the electrons are held, the harder it is, or the more energy it takes to remove an electron from the atom. Here is just a picture of those trends that we just talked about. Notice we have fluorine over here, tiniest atom. Cesium is this large sphere down in the corner. Notice the opposite trends with ionization energy. It's extremely hard to take an electron from fluorine. It's holding on to those electrons tightly. It wants to gain electrons. It doesn't want to lose one. But with cesium, very easy to take one away because it wants to lose one. Cesium's a metal. It's an alkali metal. It wants to lose one electron to become a +1 charge. The other two periodic trends we're going to look at is electron affinity and electronegativity. Knowing these definitions is really not that important. This is more just for your information. We'll talk about electronegativity a little bit more in forthcoming chapters and focus on the definition of that at that time. The important thing to note here is that both electron affinity and electronegativity follow the same trends as ionization energy, where they are decreasing down a group and increasing across a period. So here's a summary of all of those trends. You have electron affinity in purple, ionization energy in blue, and electronegativity in green. Notice all of those arrows are following the same trend, going in the same direction, whether increasing up a group and across, where atomic radius in pink goes the exact opposite direction. Atomic radius is the trend that you're going to want to focus on in this chapter. If you know that trend, then you just need to know the other three go the opposite direction. So here are some example problems that we'll be looking at in class using those trends.